All right, so we have a test on Tuesday, right? And I have put together a review of topics to go through. I'll hand this out once we get through with what I want to do today. And you'll see, I've kind of laid it out for you. I think you'll like it. Everything that we cover today, all right, is not on the test. However, this is a big however. On the test, I will ask you towards the end, the problems towards the end are going to be, does this series converge? Does it diverge? I've told you that we're only going up to the integral test, right? If you want to use the comparison test on the test, that's fine, because sometimes it's easier to do it this way. But everything I will give you can be done using something else, integral test, or as you'll see today, I'm going to do an example where we'll look at it, we'll do the integral test, and then we'll do it with the comparison test. We'll get the same result both ways, but one's much easier than the other. So everything we use today, you're allowed to use on the test.
Is it riskier?
No. 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 All right? Does that make sense to you? I mean, you should be able to do everything I put on the test with what we did up to last class. But you're free to use this as long as you say in your explanation, I'm using the comparison test. All right, so here's what the comparison test says. And this is on your sheet of paper. I just kind of rewrote it up here so we could just talk through it again. First of all, you have to be looking at a series where you have positive terms, or we should say non-negative terms. And what we're going to do is we're going to take a series that we don't really know what it's doing, so we're focusing all of our attention on a series where our series is actually the sum of the pieces of this sequence A sub n. And we don't know what it is. So we compare it to a different series that we do know something about. So there's 3 different comparison tests, all right? Depending on what you have, you'll determine which of these you want to use. So suppose that you choose another series, all right, that converges that you're going to compare this to, all right? So you look at that, you say, you know what, that kind of looks like this thing, and it converges. Then if you can show that this inequality is true, that all of these guys are smaller than all of these guys, then your series in question must converge also. So notice the inequality is that you have to show that your pieces of your series are smaller than the pieces of this series, yes? Now, let's say you look at your series and you go, that kind of looks like some series here, but the one you're comparing it to is a divergent series. Then you have to show the inequality backwards. You have to show it the other way around. You have to show that all your little guys are bigger than all of this one's little guys, which means that your series should be bigger than that series, and if that one diverges, then so does yours. Now, sometimes these are easy to do, sometimes they're hard to do, depends. This inequality is not always easy to show. So we get the last version of the comparison test, which is called, I don't know if it says it on there. I don't think it does. This last one right here, we call the limit comparison test. Okay? We call this one the limit comparison test. And that's because we are going to use a limit, all right, to figure out what happens. So look, this is very different than these two. You still have the series that you're trying to figure out. You still have to come up with another series to compare it to. But instead of trying to do the inequality, all you have to do is take the limit of the 2 sequences on top of each other. And it must be the A sub n sequence, which is, can you all scoot back? And then everyone scoot back. I feel like I can't stand here because I'm like right in the way. Do y'all mind? Thank you, thank you, thank you. That'll work. Kiki already got me sick, so I'm not, it's not that.
Merry Christmas.
Yeah, I appreciate that.
No, don't do that. Happy holidays.
All right, so we are going to do the limit of the sequence, right? This piece of what we're interested in, divided by the sequence of the thing we're comparing it to. If this limit turns out to be a finite positive number, That means it can't be infinity. If this turns out to be a finite number, then whatever the one we're comparing it to does, ours does. So they both do the same thing. If this limit is a number, they both diverge together or converge together. Understand? Yes? We'll have to see this in action, but that's what we're going to do today. All right? So I'd like to start with something we should all recognize. Hopefully. What should I start with? How about this? Does this converge or diverge? Question. Sum n equals 1 to infinity of 1 over 2 plus 3 to the n. So if you saw that on a test, what would you do first? Probably the nth term test, which is the first test we ever like to do. And that one, nth term test, all you do is, what? Take the limit as n goes to infinity of what? Of the sequence of this right here, okay? And it's pretty obvious that goes to 0, right? So the test fails, right? But that would be the first thing we would probably do. So this fails. So we move on. Is that a geometric series? Not quite, right? Not quite, because the 2 down here, right? I mean, we do have the n in the power, which is what we like to see for geometric series. But the 2 plus 3 to the n, that causes a bit of an issue. If the 2 wasn't there, would you agree that would be geometric? Yeah? So the 2 is causing an issue. So it's not geometric. Is it harmonic? Linear over, constant over linear? Nope, that's not linear. Is it p-series? No, because p-series, the n was in the base and the power was fixed, right? So it's not a p-series. Is it telescopic? So is there a way that maybe you could write that out where you're going to get like something, addition and subtraction? Probably not. Do y'all understand that? So I don't see anything. How about integral test? Do you want to integrate this? Like if that were transformed into a function of x, do you want to integrate that? You might be able to do that. Not very interested in it though, personally. I don't want to integrate that. So maybe we can compare it to something. 1 over what? What does that, that looks a lot like, comparison. That looks like a lot like sum n equals 1 to infinity of 1 over 3 to the n. Right? The 2 really doesn't have that big of an impact. As the n gets big, right, the 2 is pretty insignificant. So maybe I can compare it to this. And what is this series? I mean, if you're going to compare it to something, you better know what this is, like what it does. What is this? Geometric. Okay, it's geometric. Why is it geometric? It's the power is, the n is in the power, right? A p-series, just so you see the difference. A p-series would look like this. N to the third, that would be a p-series. 3 to the n is going to be geometric because it's like an exponential function. This one is a power function. All right, so if it's a p-series, I know that my p-series, I was supposed to get p-series if I wanted to find out what they added up to be. I had to make it look like this. Remember that? That's what a geometric series looks like. Did I say p-series? I did say p-series. Sorry. I'm just a big asterisk next to today. Okay? I'm doing my best up here. All right. So you're going to have to figure out what the R would be. What do you think the R would be for this geometric series? 1/3. Right, that's the same thing. And now, of course, this doesn't look like this, right? We'd have to add like -1 + 1 and get it to work out. But am I even concerned with what it's going to add up to be? All I'm concerned about is the fact whether or not this converges or diverges. So what does it do? What is R in this problem? R is 1/3, which is less than 1. And what do geometric series do if the R is less than 1? Converges. Okay, so here's where we are. I have a series. I didn't know what it did. So I chose to compare it to this series, which turns out to be a convergent geometric series. So whenever you have something to compare it to that's convergent, what inequality do we need to show? This one has to be what compared to this? Less than. Less than. So this one right here is our A sub n. And I'll use this one right here. Well, I'll use this right here. This is our B sub n, right? So the sum of the B sub n's, that's the one we knew what happened. And this one is the one that we want to know what happens, yes? So I just wrote this on the board a minute ago. I had comparison test. I had 1, 2, and 3. Which case are we looking at? 1, 2, or 3 here? We're looking at 1, right? We're comparing it to a convergent series. So right now, what I want to do is I want to show, right, that the A sub n's are less than or equal to the B sub n's eventually. As n gets big, that inequality will continue to stay true. All right? That's what I want to show. So I write down 1 over 2 plus 3 to the n less than or equal to B sub n, which is 1 over 3 to the n. I didn't mention this in the beginning because hopefully it's obvious to you. These two sequences, A sub n and B sub n, were positive sequences, right? You're never going to get a negative number here. If these are not positive, you can't use this test. So to show that that's true, we just work with the inequality. So in my homework lectures or homework videos, I call it cross-multiplying, but it's not technically cross-multiplying. You're going to clear a fraction zone. What's going to wind up happening is that the 3 to the n is going to appear on the left, less than or equal to the right side, 2 plus 3 to the n. Yes?
That was the question I had yesterday when you left.
Oh, when I abandoned you? Yes.
So technically you could do that and then just kind of forget about the bottom.
Yes, but please understand what you're doing, okay? What you're doing is multiplying by 3 to the n here and 3 to the n here, right? These cancel. Then you're multiplying by 2 plus 3 to the n here and 2 plus 3 to the n here. Gosh, what's up with my n's over there? These two cancel. And so what you're left with is on the left side, 3 to the n, on the right side, 2 plus 3 to the n. That's what's actually happening algebraically.
Will there ever be a situation where that doesn't work?
If there's more than one term over here, so like if you ever have something like 1 over n plus 1 over n squared less than or equal to, I don't know, 1 over 3 to the n, you can't do that because there's two terms. And plus, it's not really cross-multiplying. That's just a shortcut name for something that's... It's not cheating, but it's just kind of like, it's a shortcut, but it's not supposed to make a lot of sense. It's just supposed to be easier, right? But what you lose in that is what's actually happening.
It's just an evaluation.
Yeah. Okay. So may I continue? Is that true? Is this always true or not? Or I need it to be eventually true. Just subtract 3 to the n on both sides. And you get zeros less than or equal to 2. Is that true? I hope so. Or else we got bigger problems, right? All right, so that's true. So I've shown the inequality is true. So what now? Therefore, I can draw my conclusion. All right?
So you don't have to.
You don't do anything else. Okay? We wanted to show this was true. We worked through it, and at the end we got a true statement that we can all agree on as being true. So this inequality is always true. And since it's always true, my series, go ahead, Zach. You sound like you still had a question.
I was trying to figure out why that was true at first, because I thought the a sub n was the 2 plus 3. I see that it's greater. I didn't see that it's less. So that's what.
Say again?
2 plus 9 is the a sub n.
This is the a sub n. 1 over this. 1 over this.
If the a sub n is supposed to be less than the b sub n, it's not.
This is smaller. 1 over 2 plus 3n is less than 1 over 3 to the n. Now, I showed that this is true by moving it all the way over here and just saying that that's true. But just think about it right here. What's bigger, 2 plus 3 to the n or 3 to the n? Which one of those is bigger? This bottom or this bottom? This one. Okay, so 1 divided by that should be smaller than 1 divided by this. If the denominator gets bigger, this fraction gets smaller. It's not always easy to see that, though. So what we do is we do what I just did, and we get to something that goes, ah, yes, now that's true. All right? Is this all okay? Now, what I'd like to do now is the same exact problem, but this time I want to use the limit comparison test and see if it works, which is the third version, right? The third one on there. So how would I apply the limit comparison test to this? I still have to compare it to something, don't I? I still have to compare it to something? So you want to compare it to the same thing? Let's compare it to this. We know that this converges, right? This is a convergent geometric series. We still have that this is a sub n. We still have that this is b sub n, right? But instead now I'm going to set up a limit of the ratio of those two sequences and hope to get what? A constant, a positive constant. So I'm going to set up the limit as n goes to infinity of a sub n over b sub n. Everyone clear on where those two pieces came from? Right? If you get it backwards, you're going to get, it's not going to work. Okay? It has to be the a sub n over the b sub n. Now, before I actually take a limit, let's just flip this. This is a complex fraction, right? So just bring this fraction, flip it up. And so this is really the limit as n goes to infinity of 3 to the n over 2 plus 3 to the n. And now let n go to infinity, and what do you get? Infinity over infinity, so L'Hopital, right? Now again, we are not going to switch it to x. We already talked about that last class. We're just going to go from there and say, all right, that's limit by L'Hopital's rule, n goes to infinity. Now carefully tell me what the derivative of the top is. 3 to the n natural log 3. Go back. Cal 1 derivative of a to the x is a to the x times natural log a. Derivative of the bottom. Derivative of 2, gone. Derivative of 3 to the n, well, we just did that, right? 3 to the n, natural log 3. Again, right? The 3 to the n's cancel, and you get natural log 3 over natural log 3, which is 1, which is a positive constant. That means we're happy. Because that means that whatever the series we compared it to does, our series does. Understand? So I'm going to draw my conclusion now. Therefore, our series n equals 1 to infinity of 1 over 2 plus 3 to the n converges by the what? Limit comparison test. Which one of those do you think was easier? You think you like the second one better? Okay. So that's why I'm saying, like on a test, I really don't care what test you use as long as your test is done properly and you draw the right conclusion. I don't care what test you use.
We have to name the test.
You do have to name the test. You have to tell me what you're doing, because if not, I have to guess what you're trying to do, and that could not bode well for you if I'm trying to determine what you're scribbling all over your page. Yeah. Okay, no questions? We're good? All right, let's take a look at another one. This one's kind of cool. Next one, same thing, converge or diverge. Let me know. Sum, n equals 1 to infinity. 1 over 3 plus root n. Anybody want to tell me what their gut instinct is as to what this does? What goes to 0? The sequence here goes to 0? That would be the nth term test, right? Which means what? Nothing, right? But I'm saying, does anyone want to tell me, like, gut instinct, do you think this converges or diverges? You think diverge? All right, well, let's figure out what it is. What would you like me to compare this to? I mean, hold on, I should step back. This isn't geometric, right? It's not telescopic, collapsing, harmonic. It's not harmonic, right? Is it a p-series? Almost, right? Almost. If the 3 wasn't there, it'd be a p-series, wouldn't it? So why don't we compare it to a p-series, right? Y'all with me? Okay, so let's compare it to, I'll do my comparison one in red here. You tell me what you want me to compare it to. 1 over, I heard 1 over n and 1 over root n. What do you want? Root n, let's take a vote. Root n? N? Okay. So we'll go with root n, all right? Only, why? Because if n is big, does adding 3 to a huge number really matter? So this is really kind of behaving like this one does, right? I mean, that's what we think, right?
We can't write it as 1/2. 1 over 1.
Yeah, we could write that. Well, we're going to, because we need to know what this does. And to help you see what it does, I'm going to rewrite it as 1 over n to the positive 1/2, right? And this is what type of series? P-series? Last class, p-series? With p being 1/2, which is, what are we looking at? If that's less than or equal to 1, what happens if it's less than or equal to 1? It diverges. So I was talking to a fellow colleague of mine, you might know him, Mr. Roy, Mr. Matt Roy. Anyways, he and I like to talk about a lot of things when it comes to the way we approach some things, even though we're very different instructors. And whatever your feelings are about Mr. Roy, he's helping you because he thinks you should be allowed to use that sheet on your test. Okay? I asked him if he allows his students to use these on the test. So you're allowed to use this on the test, no penalty. All right? Everybody. All right? Force them out for him.
So he's not dead, though.
I mean, you can't do it anyway, just he's not here.
No.
Okay, that's not the, oops. Let me clean that up. I'm sorry. I'm sorry. I need to get back on track.
Professor?
My head's
Is this
full.
gonna be, is this comparison test gonna be on our exam?
You could use it, right?
Yeah, that's what I was saying in the beginning. All this, everything on your exam can be done without the comparison test. But if you want to use it, you can.
Do we get bonus points for using it?
I don't know.
You don't know.
I don't know. I hadn't thought about it. All right, so we are comparing this to a divergent, right? A divergent series. So if you look at the three things we had, 1, 2, and 3, which one of those would it fall into? The second one, but we could also do limit comparison, couldn't we? We could also do the third one. The third one we can do on any of them. So why don't we try the second one and see how it works out? All right. The A sub n we have is this. The B sub n we have is this. Of course, they're both greater than or equal to 0, so I can do the comparison test. And so what is it that I want to show? I want to show A sub n is greater than or equal to B sub n eventually. As n gets big, that inequality will hold. So I want to show that 1 over 3 plus root n is greater than or equal to 1 over, what, root n? That's what I want. Because this is divergent, I have to show that inequality as opposed to the other one. Questions? Do that little thing? Shortcut? What's the new inequality after the shortcut? Root n greater than or equal to 3 plus root n. Can you do anything there? Subtract root n on both sides. Uh-oh. Uh-oh. 0 is greater than 3. Now, pay attention, because even though I'm all medication on a bunch of medication right now, I still know what I'm about to say is important. All right? What is your conclusion here? What do you think about that? This inequality doesn't hold. What does the test say? The test says if this is true, then they both diverge, right? But if this is not true, it fails. The test fails. That means you don't know. This is like the Nth Term Test failing. See, this is not true. Do you all agree? So this test failed. Just because it... See, what you're trying to do is determine whether or not it diverged, right? For it to diverge, you had to have this happen. It didn't happen, but that doesn't mean that it still doesn't diverge. It could. It's just this test did not work to tell you that. Do you understand? If you draw this conclusion on a test and then you say, okay, therefore it converges, you'll be wrong. Y'all see it? Subtle? So what are we going to have to do? We have to pick something else. We either have to compare it to something else, or we have to maybe do the limit comparison instead, right? So what I'd like to do is I'd like to think about what it is that caused the problem. We were sitting here, right? And we did this little thing. And at this step right here, right? At this step right here, these two canceled. And so I got 0 here and root 3 here. Yes? Yeah? What if what I really needed, right, was for this side to be bigger than 3, right? This side bigger than 3, and this test would have worked. Yeah? So where did the root n come from? Right there? I need to use something bigger than root n. Now, that's a good, you're almost there. We can't use 4 plus root n because we're trying to figure out what 3 plus root n is, right? So, but you're almost there. There's a couple of different ways. What did you say, Kiki? N over root n? You just need this to be a little bit bigger than root n, right?
Plus 1? What? N plus 1?
How about just, instead of root n, how about just n? Which was the only, you were the one who suggested that, right? N would work, maybe. But you said 4 plus root n. How about just 4 root n, right? Then when I do this, this would be what? 4 root n. When I subtract, I get 3 root n, bigger than 3, and that would be true as n got bigger. So look, even though you're stuck, if you think about what made it fail, that will help you figure out what you should compare it to instead. I hope that made sense. So I would like to start it over.
Why couldn't we do 4 plus root n?
Because we don't even know what 3 plus root n does. So how are we supposed to compare it with 4 plus root n? Right? Okay, so new comparison here. So I have to start over with a new comparison. And what do you want? Do you want to do the 1 over 4 root n, or do you want to do the 1 over n? You like the 4? Y'all like the 4? Yes? The 4? I like the n, sorry. Because I think the 4, you do the 4, but I like the n because I want to see there's one part of the algebra that's going to get a little weird with this. Okay, what does this one do, everyone? This is divergent. Why? Why is this divergent? I haven't heard what I want to hear yet. Did you say it? Harmonic? Okay, I just didn't hear it. This is harmonic. A harmonic series is the same as what? P series with P being 1, right? So you could say this 2 ways. This is a P series with P being 1, so it diverges, or you could say it's a harmonic series. So since that is what we're comparing it to, this is our B sub n, then we still want to show that same inequality, right? That our A sub n's are bigger than or equal to our B sub n's. So we want to show that the 1 over 3 plus root n is greater than or equal to 1 over n. You following me? Now do the little thing with the inequality. And you get what? N greater than or equal to 3 plus root n. Let's try and get all the n's on one side. This is where I said the algebra, this can be a little bit tricky. That's why I wanted to do this one. N minus root n bigger than or equal to 3. Do you think that that's always true? Is it always true? It's not true for 1, right? Is it true for 2? It's not true for 2. Is it true for 3? No? How about 4? 5? Or you see what I'm doing? I'm plugging the numbers in mentally, thinking through them. Are they bigger than 3 when I do this side? But eventually, is it? Eventually. So I need to convince myself of that. Here's how I'm going to do it. This is what we're getting as n gets big. What we really have is something that looks like infinity minus infinity here, right? And the way to try and figure out what happens when you have infinity minus infinity is to try and factor it. So do you agree I could pull a root n out of both of these? Right? Root n out of both of these. Root n times root n is n. Root n times negative 1 is negative root n. Now what happens as n gets big? This goes to infinity times this goes to infinity minus 1, infinity. Is this going to get bigger than 3? Absolutely. All right? It is, right? It has to. So I'm going to say yes, check, because this is eventually going to happen, isn't it? That's eventually going to be true? I'm not really even concerned about where it happens, just that it eventually does. And at some point after, wherever it is, at that point on, this is always going to be true. So that's it. I can draw my conclusion now. Therefore, series n equals 1 to infinity, 1 over 3 plus root n diverges, right? Diverges by comparison test. So I chose to use, in the comparison test, the second one. I did not use limit comparison, did I? Would you like to try this problem with limit comparison? Or are you happy you think you could do it? Yes?
Does the limit comparison at all fail?
I don't know. Depends on what you compare it to.
So it's the same thing, it can fail?
It can fail, yes. So, I don't know. Yeah, let's try the limit comparison. I'm curious to see what happens. Is that all right with you? Okay, let's try this problem with the limit comparison test. And let's try it with that 1 over root n that didn't work for the comparison test, right? Let's try it with this, but limit comparison instead of just a straight, which some books call it direct comparison as opposed to limit comparison. So I'm going to take the limit as n goes to infinity of what? 1 over 3 plus root n, that's a sub n, divided by 1 over root n, which is really the limit as n goes to infinity of root n over 3 plus root n. It's infinity over infinity. So L'Hopital. I was trying to remember in the last lecture, I was trying to find it in the video. I'd used this phrase, without loss of generality. Does anyone remember me saying that? No? I thought I said, I couldn't find it on the video. Never mind if I didn't say it, then forget it. All right, so derivative. What's the derivative of root n? 1 over 2 root n? What's the derivative of the bottom? Oh, wow. 1 over 2 root n. Which is just 1, which is a positive constant. Which means what? Whatever the red one did, ours does. Boy, that was much easier, right? So, therefore, right, therefore that converges by the limit comparison test. So now, in retrospect, we should have done that first, right? But that's part of what I want to show you today, is how each of these are a little different.
If we're going to be using that type of comparison test, we don't necessarily have to do it in that order. We don't have to do it like
That is right. That's a good question. Ron's asking, when you're using the comparison test, do you have to do, try one first before you do limit comparison? No. You can start with limit comparison if you want. I wonder if this would have worked if we would have tried the limit comparison on 1 over n. Would it have worked? So what would have changed? This would have changed to what? N. And then this would have changed to, ooh, this is good. Watch this. N. And then the derivative of the top would have been what? 1. And then when you flip that around, look what happens. Limit n goes to infinity of what? 2 root n. And where does that go? Infinity. And the test would have failed. Do you see that? If you would have done limit comparison with 1 over n, the limit comparison test would have failed because this would have gone to infinity, which is not a positive constant. And so your test fails and you would have had to have tried something else. Yes or no? But 1 over n did work if we used the inequality, right? The a sub n greater than or equal to b sub n, that did work. But the 1 over root n didn't work when we tried the inequality. So you can see this can become a cluster, right? I mean, you pick in something, you try it, you're like, it's not working. But if you try it another way, it will work. So it all depends on the test you apply. Any questions?
So most of the tests don't tell you, like if they fail, they don't tell you.
They don't tell you anything.
So you got to do it until they.
You have to do it until you draw the correct conclusion. What the test tells you, you're allowed to conclude. If the inequality, like on the 1 and 2, if the inequality holds, you can conclude. If it doesn't hold, you go to something else. You have to keep going until you find something that's true. Yes. All right, well, we should try something else. All right, so look, let's take a look at this real quick. What's your instinct here? That this is harmonic looking? So A and B here are constants. All right, I should write that down here. A and B, constants. And let's not make it confusing, so that, because I know we could possibly make this spit out negative numbers. Let's just make sure that these are both positive numbers. Or just A, so no one causes any problems. Just A, as long as A is a positive number. Then I told you that all you have to ever tell me when you see a fixed over linear is what? Harmonic and it's diverging, right? But let's just show that it's true. Because I said it's true, but let's just show it's true. And I'm going to do it by comparing it to something like, I don't know, something I know for sure is divergent, which is 1 over n. Right? And I'm going to use the limit comparison. So I'm going to do a limit comparison where this one right here is my b sub n, and this right here is my a sub n. They're both positive, right? That's why I had to make a positive here. This will be positive eventually. Even if you give me a big, negative b number here, I can get, this will eventually be a positive term. A will get big enough and it'll overwhelm whatever's behind it. So let's take this limit. What's the limit? N goes to infinity of this guy over this guy. So you'll wind up flipping. You'll get n over an plus b. Do y'all see I put the two fractions but flipped them? Okay. And then let n go to infinity, L'Hopital one time. And you get what? 1 over a. And a is a constant, and a is positive. So this is a positive constant, right? This is a positive constant. So therefore, whatever this does, this does. So therefore, sum n equals 1 to infinity of 1 over an plus b diverges by the limit comparison test. But I kind of already told you I was doing that, right? So that just proves what I told you could do. I told you several classes ago that you could just look at that fixed over linear and say divergent. But now that shows, yes, you can do that for sure. Question?
So what happened if A is like infinitely small, like this is like 0?
It doesn't matter how small it is as long as it's positive.
It'd still be a positive.
Yeah, as long as that's a positive number and it's stuck, it's fixed, right? Then 1 over that's still a positive number. Might be huge, but it's, see, we're not, the only thing going to infinity is the n, not the a. All right, let's try another one. Dun, dun, dun. It's kind of fun, huh? Starting to feel better already. So we don't want to narrow our focus too much. You might start with the Nth Term Test, then look, is it geometric, is it telescopic? And I think I said this in the beginning of this chapter. I said this chapter is kind of like the integration, in that once we get through all the integration, someone gives you an integral, you have to figure out which technique to use. This is kind of like that in the sense that when you look at a series, you're like, I got to figure out, like, does it look like something that I should know? Is it a geometric series? Is it a p-series? You know, like, do I do a comparison? Do I do a limit comparison? Do I do an integral test? Right? So what do you think? Okay, you want to do a limit comparison? It's been pretty successful, hasn't it? So far? I mean, we did have it not work a second ago, but it would just matter. What would matter here is what it is we're actually comparing it to, though. What do you want to do? What do you want to compare it to?
Square root of n over n squared, and then that becomes.
So you're thinking that if n is really big, the 1 doesn't matter? Ron, is that what you're saying? That's what you're saying?
Yeah.
I agree that that's a good place to start. I mean, it may turn out that this crashes and burns, but that's a good place to start. Now, let's figure out if we know what that does. We have to, there's no sense in comparing it to something that we don't know what it does, if we don't know what it does. So what is this? It's a p-series. It's 1 over n to what power? This is n to the half, and then you take away 2, that's negative 3/2. So this is positive 3/2 down here, right? So this is a p-series. P-series greater than 1 converges. You sound like you know what you're doing over there. It's good. All right, so let's do it. Let's see. And you said you wanted limit comparison, right? Yep. Okay, so I'm going to let everyone know I'm about to use a limit comparison. Here it is. I'm going to take the limit as n goes to infinity of a sub n over b sub n. And I'll write it out. I'm not going to try and get ahead of myself here. Here's a sub n over, now b sub n, I probably am not going to use this. I'm probably going to go back to this version right here, because it had root n in it, and that one has root n in it. Root n over n squared. And flippy, oh, it's going to be 1, isn't it? Let's see. This is going to work. I'm not on medications. I'm just saying that to make an excuse for my absurd behavior up here. Okay, let's see. N squared over root n. So that's just flipping. And you see the root n's cancel. And n squared over n plus 1, infinity over infinity. L'Hopital 1 time. You get 2n over 2n, which is just 1. And that's what we want, right? We want this to happen. Good. Positive constant. The happy face is optional. Extra credit, yes. Yes. The better the happy face, the more extra credit. No. All right, so what do we do now? Draw the conclusion. Actually write down what it is that you're, going to tell me the answer is, right? Therefore, series n equals 1 to infinity of root n over n squared plus 1 does what? Converges. That's it. That was pretty good. I like that one. Now, who knows? If you would have picked a different comparison, a different thing to compare to, I can't promise you it would have worked out that nice. if you try the nth term test, just to see, like, straight off if this thing, what it does. Remember the nth term test, right? The most basic one that usually fails. If you try that, you get infinity over infinity. You can try L'Hopital. It's probably going to get kind of ugly, though. So it's almost like nth term test might not even be worth it to go through the trouble of trying to figure out what it does. But I don't think that it goes to 0, right? Because if it goes to 0, the test fails, right? The nth term test fails if that thing goes to 0, but I don't think it does. Why? What's my argument to why that?
Exponent versus geometry.
Yeah, on the top you've got, look, this is an exponential function, 2 to the n. That thing grows very fast. Multiplying it times n makes it grow a little bit faster. And on the bottom you have n cubed, which grows fast, but not as fast as 2 to the n does. So I think this thing goes to infinity. Like if you were just do nth term test, I'm pretty sure that thing goes to infinity, which is something other than 0. So it should what? Should diverge. Well, if you wrote it all out, maybe, like, I think that the top exponent, but we need something a little more concrete than that. So we have two choices here. Do you want to go for nth term test, or do you want to try to do a ratio test and a comparison? You want to do the nth term?
No, the limit.
The limit comparison. You want to do a limit comparison? Then what do you want me to compare to, though? Yeah?
If you were to do the nth term test, would you have to like derive? No.
You would have to, for L'Hopital, you'd have to take a derivative on top, which would be a product rule.
But you could.
You want to try n over n cubed? That's
Yeah,
one.
that'd be n times 2 to the n over n.
But when you're comparing it to, if it has like one less n, does that make a difference? Does it need to have like all the n's?
No, it can be whatever you want it to be. Just you want to pick it smart. You want to pick it to be something that is something close to what you have, that you think behaves somewhat the same way.
So if it's just n over 2n over n cubed, then if you cancel out, it's 2n over n squared.
I'm hearing a couple of different things. If n is really big, does that one matter much? No? So could we at least all agree on this? That it's very similar to that?
But we don't know what that does.
That's right, we don't know what that does. But let me clean it up a little bit. Do you agree with this? I could put a 4 down there if I want, right? That's because this is times n, that n cancel, and you get that, right? But again, we don't know what this does, do we? This is not a geometric series, not a harmonic series, not a p series. It's kind of a combination of a couple of things, right? Like 2 to the n is like geometric, but like 1 over n squared is p series. What do you think this behaves like? What? A geometric p? Which one do you think is dominating this? The 2 to the n or the n squared? The 2 to the n? 2 to the n?
We can graph, can we?
We could.
Like in our calculator?
To figure out which of these, or what do you mean? Like graph the whole thing?
No, include them separately.
Uh-huh.
The,
You could. But we should all know that 2 to the n is an exponential function, n squared's quadratic, and that 2 to the n grows much faster, exponential growth. I'm going to go out on a limb here. This is all great and stuff. I don't think the n squared really makes that much of a difference here. I really think that this is really more like 2 to the n. That's what I think this thing behaves like. At the end of the day, I really think that's what it behaves like. Because the n squared, although it gets big, it's not as big as that is, the 2 to the n. Which one? Do the n term test? You could do n term test on this. You'd still have to take derivative top and bottom, right? Which is okay. Derivative top. Yeah, I like that idea. I really do like that idea. But I'm going to stick with this. I like that idea, though. I really do. I'm hoping I can get it with this. Okay? You all with me still? I'm going to go for it. I'm going to go for this, okay? Now, do I even need to talk about what that one does? I mean, we all know what this one does, yes, hopefully? That diverges, right? That diverges for sure by the nth term test. Because if I take the limit as n goes to infinity of that, it does not go to 0. It goes something other than 0, and that means it diverges for sure. So by the nth term test, that diverges. So I'm comparing this to that. And you want to do limit comparison, right? I have my doubts here. I really do have my doubts whether or not we're going to get it on this. Limit comparison. So I'm going to take the limit as n goes to infinity of this, n times 2 to the n over 4n cubed plus 1 over 1, wait, not 1 over. It's not 1 over. What is it? It's just 2 to the n. Right? Which you could say is over 1. And when I flip, oh, yeah, it's going to work. No, it's not. It's going to fail. What's it going to do? Let's see. I'm not going to get a positive constant. Limit n goes to infinity. So when this flips, right, when that flips, it's like a 1 over 2 to the n like this. And those cancel. Bless you. And you just get n over 4n cubed plus 1. Any questions on that? Sure? And so when we look at this, what's that limit? You have to do L'Hopital one time maybe? If you do L'Hopital one time on that, what do you get? L'Hopital here, and it goes to infinity. 1 over 12n squared. And that turns out to be what? 0. Is that a positive constant? It's a constant, but is it positive? It's not positive, which means it failed. So 2 to the n did not work.
How many times can you do L'Hopital?
You can only do L'Hopital as long as you have 0 over infinity over infinity. As soon as you no longer have that form, you must stop. So like here, we no longer have 0 over 0 or infinity over infinity. We have fixed over infinity. So we stop. Well, that sucks. So going back, all right, let's see. The problem that we ran into here, let's see if you can recognize this. When we did this and we did the flipping, right, the 2 to the n's canceled. And what I was left with was a linear expression on top in n and a cubic expression in n down here. And then when we did L'Hopital, the power of the top went down, the power of the bottom went down. We were left with a constant over a quadratic. Yes or no?